Welcome once again to Physics Medicine online tutorial class. I am your teacher, Mrs. Okuma Ijoma. Now, in our previous class, we talked about reflection of light. And we found out that light can be reflected in a plane mirror and also in a curved mirror. We talked about reflection of light at plane mirror surfaces and also at curved mirror. We looked at reflection of light in concave and in convex mirror, and we equally talked about their applications. Now today we want to look at refraction of light through rectangular glass block, or you call it rectangular glass prism. Now our specific objectives: by the end of the lesson, students will be able to, number one, define refraction. Secondly, state the laws of refraction of light. And thirdly, describe how the law of refraction can be verified in the laboratory using a rectangular slab and optical pins. Now, what do we mean by refraction of light through rectangular glass block? We are going to define refraction. What is refraction? Refraction is the bending of a light ray as it crosses the boundary between two media of different densities, thus causing a change in its direction. We take it again. We say that refraction is the bending of a light ray as it crosses the boundary between two media of different densities, thus causing a change in its direction. So whenever we are talking about refraction, two different media must be involved. What do we mean by that? We say two different media of different density. For example, the ray of light might be moving from air to glass or air to water, whereby you know that your air has a lesser density compared to your water. If it's in the case of wave, we say that the ray of light or the wave can travel from a shallow water to a deeper water, whereby a shallow water has lesser density than the deeper water. So in refraction, as the ray of light, the incident ray of light, meets the boundary between the two different media, the ray will be refracted. And as the ray refracted, there is a change in the direction of the ray. Now, where do we observe the phenomena of refraction in our everyday life? We can observe them, number one, at the bottom of a clear river or pond, which appears shallower than it really is. When you have a clear pond or a clear water and you look through it, you'll be seeing the bottom of that clear water, and the bottom of that water appears to be nearer than the normal depths. That is one of the effects of refraction. Another one, a rod or spoon appears bent or broken when it is partially immersed in water or any liquid. So you find out that when you put your spoon inside a water, when you immerse it partially inside a water in a glass, and you look at it, you find out that that spoon appears as if it is bent or as if the spoon is broken. Now let's look at this diagram. Look at this pencil inside a beaker of water. Now, as a result of refraction, you can see how the pencil looks like. The pencil appears as if it is broken, and this is as a result of refraction. Then another one, letters in print, seems to be nearer when we place a thick block of glass over them. Now when you use your rectangular glass prism and place it over a print, it appears as if it is nearer than the normal what? Depth. So these are the effects of what? Refraction. They are the effects of what? Refraction. Now let's look at this diagram again. Now from this diagram you can see you have two different media. You have your vacuum, then you have your what? You have medium A and you have medium B. The other one is vacuum, which is an empty space. Then the other one is your glass. Now look at the diagram again. You will see your straight line representing your what? Normal. Normal is a straight line of an angle of 90 degrees. Now you can see the incident ray represented by the letter PO. Now this is the incident ray of light from the first medium, that is the vacuum. Now on getting to the boundary, you can see the boundary between the first medium and the second medium, which is your glass. The light was refracted, no more reflection. The light on entering the second medium, the ray of light refracted, and you can see that this ray refracted towards the normal. Take note. So when an incident ray of light moves from less dense medium to more dense medium, the ray is being refracted towards the normal. The ray refracted towards the normal. And in this case, you can see your angle of incidence, I, which is the angle which the incident ray makes with the normal. Then you can equally see your angle of refraction, which is the angle that the refracted ray makes with the what? Normal. Now you find out we say that this incident ray refracted towards the refracted ray refracted towards the normal. And in this case, the angle of incidence, I, is greater than the angle of what? Refraction. So take note, when a ray of light is moving from a less dense medium to a more dense what? Medium, the refracted ray moves towards the normal. The ray is refracted towards the what? Normal. Now let's see. The angle of incidence, as I've said, is the angle which the incident ray makes with the normal to the surface at what? O. Now, as I've said again, we say that when the incident ray of light moves from a less dense medium, such as air or vacuum, to a more dense medium, such as your glass, that the ray is refracted towards the normal, and the angle of incidence will be greater than the angle of what? Refraction. Then conversely, if the light travels from a denser to a less dense medium, the refracted ray will do what? Bends away from the normal, and in such a case, the angle of refraction will be greater than the angle of what? Incidence. So when the ray of light moves from denser medium, for example from glass to air, the refracted ray will do what? Bend away from the normal. While in the other case, it will bend towards the normal. Now let's look at this diagram. you can see the ray is moving, in this case, from water towards air, and water is more dense than air. Now you have your incident ray. On getting to this boundary, it is refracted away towards the normal. So you can see in this case now, your angle of incidence, which is from here to here, is greater than your angle of what? Refraction. So the ray bends away towards the normal. Now we're going to look at refraction through rectangular glass block. Refraction of light through what? Rectangular glass block. Now we look at this diagram. Now this is a rectangular glass block presented with the alphabets A, B, C, D. Presented with the alphabets A, B, C, what? D. Now you look at your normal, the straight line O. Now you look at your incident ray PO. Then you look at your refracted ray O, represented by O. Then you see your another ray, which we call the emergent ray, represented by what? A. So you can see that the ray of light moving from air, the incident ray, on getting to the boundary between the air and the glass, it will be refracted towards the normal, as we have said. Now the angle of incidence is angle I. Then the angle of refraction is angle what? R. Now as the ray is moving from the glass to the air, that is now from more dense medium to less dense medium, the ray will equally be refracted away from the normal, and here the ray emerges, and we call it the emergent ray. Then the angle, we call it the emergent angle, angle of emergence. So we look at what we have here. We say that the thick rectangular glass block ABCD, as I've explained, is placed horizontally on a thick sheet of paper. Then you draw the outline. Then you use a ray box, or you can use your optical pin to place at the angle of incidence. If you're using your ray box, a light ray from a ray box is shone onto the glass surface. I've shown you your ray box when we are talking about reflection of light at curved mirrored surfaces. Then AB along a line PO inclined at an acute angle to the normal ON, as we can see in that diagram. Then the ray is refracted in the glass slab and emerges from the side CD. Now we're going to look at the laws of refraction. The same way we have laws of reflection, we equally have our laws of what? Refraction. Can we recall the laws of reflection? In the laws of reflection, we say that the incident ray, the reflected ray, and the normal at the point of incidence all lie on the same plane. Then the second law, we say that the angle of incidence is equal to the angle of what? Reflection. Angle of incidence I is equal to the angle of what? Reflection. Now let's look at the laws of refraction. Remember what we said about laws. You must state it the way it has been stated. You don't add, you don't subtract. Now we have two laws governing the refraction of light. The first law states that the incident ray, the refracted ray, and the normal at the point of incidence all lie on the same plane. Let's take it again. The incident ray, the refracted ray, and the normal at the point of incidence all lie on the same plane. Now the second law of refraction states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant for a given pair of media. Now this second law is known as Snell's law. Is known as what? Snell's law. Where we say that the ratio of the sine of angle of incidence, that is sine I, all over sine R, is equals to what? N. That is a constant. This constant, we call it what? N. And this N is what we call the refractive index of the second medium with respect to the first medium. It is a number which gives a measure of refraction or bending of light as it travels from one medium to another. If light is traveling from air to glass, the refractive index, when light is traveling from air to glass, the refractive index is given by ANG. That is the refractive index of the ray of light moving from air to glass. Moving from where? Air towards glass. So, and is equals to sine of angle of incidence in air all over the sine of angle of what? Refraction in glass. Remember, in refraction, the ray of light passes through two different media. Now, in the case where the light ray travels from glass to air, the refractive index will be given by NGA. What does that mean? Refractive index for a ray moving from where? Glass to air. G is talking about glass, while A is talking about air. So, refractive index of a ray of light moving from glass to air will give us what? Sine of angle of incidence in glass all over the sine of angle of what? Refraction in air. Now remember our principle of reversibility of light. What does it say? That a part of a light ray is reversible. Now using that principle, we find out that the refractive index of a ray of light moving from air to glass will be equal to 1 over refractive index of a ray of light moving from glass to air. Moving from glass to air. Now, since refraction is due to change in the speed of light, we say that refraction, whenever the ray refracted, there is a change in the speed of what? Light. So since refraction is due to change in the speed of light as it travels from one medium to another, in such a case, refractive index of a ray of light moving from air to glass will be equal to what? Speed of light in air, or you call it vacuum, all over the speed of light in what? Glass. Speed of light in air all over what? The speed of light in what? Glass. Now let's see the use of optical pins in investigating the laws of refraction. Remember, we have stated the two laws of refraction. where we say that the incident ray, the refracted ray, and the normal, and the point of incidence all lie on the same plane. All lie on the same world. Now, we want to look at the use of optical pin in investigating laws of refraction. So you can see your softboard with your plain sheets. You use your thumb pin and hold your plain sheets in your softboard. We want to investigate these laws of refraction to know whether the laws are in order. Now you can see I'm using the thumb pin to hold it. Now look at it. Your glass block, the rectangular glass block or prism. Now we're going to trace the outline of this rectangular glass block. Trace the outline of the rectangular glass block. Then you label the outline and label it A, B, C, D. So you can use any alphabet of choice. Label it. Then you draw your number. The number is a straight line of angle 90 degrees. You can label it ON. That is your normal. Then you measure a particular angle of incidence using your protractor. In this case, we are measuring 40. From 90, you count 40. From 90 to 80 will give you 10. From 90 to 70 will give you 20. So from 90 to 50, you have 40 degrees. So you measure out that angle, representing your angle of incidence. And the straight line, PO, represent your incident ray. Present your incident ray. Now we use two pins. We use two optical pins and place them at that point. Make the two optical pins to be firm. Place it at that point where you have your incident ray. The two pins will not be far away from each other. You use a straight pin, a straight optical pin. Then you place back your rectangular glass block. Then you get a sighting pin. You're going to put two sighting pins to be in a straight line with the images of the first two pins, P1 and P2. So these two pins are the sighting pins. You move it along that CD until it appears to be in a straight line with the images of P1 and P2 when you view it through that rectangular prism. Make sure they appear to be in a straight line with the images of the first two pins, P1 and P2, when you view it through the rectangular glass block. Now, once you get them in a straight line, you can remove the two sighting pins. Then you draw a straight line to represent them. Remember, there must be a pinhole on your plain sheet. If that pinhole is not there, WAEC will not score you. So the two pinholes must be there. Very, very important. make sure you did the experiments by yourself. Now use a straight line to join the two pinholes. Join it, then you draw a straight line representing your normal. You draw a straight line representing your normal. A straight line will represent your what? Normal. Then you join the two other ones, and that is your OR, or you can give any labeling. Now measure the angle of refraction. Let's see. You put your protractor in the right way. From 90 you count. That is what? Angle 25 degrees. Now what do you see here now? You can see that the ray of light here is moving from air to glass. So the refracted ray bends towards the normal, as we have seen. And the angle of incidence, which is 40, is greater than angle of refraction, which is 25. Now we do it for several others. We do it for 20, 30. So for 20, you can see your angle of incidence 13. Now you find the sine of angle of incidence and sine of angle of what? Refraction. For 30, you can see your angle of refraction. For 40, the angle of refraction is 25. So as you have done that, you find the sine of angle of 40 and the sine of angle of 25. You take your readings. Now, we are going to do sine I over sine R in each of them. So at each of them, you can see that for 30, for 40, sine I, they are sine R. Now when you do sine I over sine R, for angle of 20, you have 1.5. For angle of 30, 1.5. For angle of 40, you probably have what? 1.5. Showing they are what? Constant. So from this experiment, you have seen it, that the incident ray, the refracted ray, and the normal at the point of incidence all lie on the same plane. Then the second one, which says that sine of angle of incidence is equal to the sine of angle of what? Refraction in a given pair of what? Media. That is why your sine I over sine R in all the experiments will be what? Constant. So the same experiment, we are seeing it here also. You trace out your rectangular block A, B, C, D. Then you measure a particular angle of incidence I. Now this P1 and P2 represent your what? Optical pins. The two optical pins. Now you use a sighting pin, that is Q1 and Q2. Place them in a straight line with the images of what? P1 and P2 when you view it in your rectangular glass block or your rectangular glass what? Prism. Now when they are in a straight line, you remove it, you join these two pins using your straight line. You join it with a straight line, and this straight line represents your emergent ray. Your emergent what? Ray. Why this angle is the angle of what? Emergence. Then you now join these two rays again. From here already you have drawn your normal as we have seen in our experiment. Then you join these two rays A, B. Now this one represents your what? Angle of what? Refraction. Your angle of what? Refraction. So you measure it. We do it for several angle of incidence. So let's see this table. When we did it for angle of incidence I, 20 degrees, our angle of refraction, we got it to be how many? 30 degrees. We got our angle of refraction to be 30 degrees. Then we now use our calculator and do our sin I. Now sin 20 degrees will give you what? 0.340. Now you do sin R, which is sin 13 degrees, that is 0.220. Now sin I over sin R, which is 0.340 divided by 0.220, that will give us 1.50. You put it in 3 decimal places, that because they are calculated values. Now you do for another angle of incidence to be 30. After the experiment, our angle of refraction, we got it to be how many? 20. Remember, the ray is moving from less dense medium, that is air, to more dense medium, that is glass. So the angle of refraction bends towards the normal, meaning that the angle of incidence must be greater than angle of refraction. Then you have your sin I, that is sin 30, and that will give us what? 0.5. Then your sin R, that is sin 20, gives you 0.340. Now when you do here 0.5 over 0.340, you equally get what? 1.5. Now in the same way we did for 40, sin angle of incidence of 40. Then when we do the experiment, our angle of refraction was 25. Then you find sin 40 and sin what? 25. When you find the ratio, you equally have what? 1.5. So we do it equally for 50, 60, and what? 70. And we found out that we have the same value for our sin I over sin R, and that is the refractive index of the glass when the ray of light is moving from air to glass. So you find out that you have a constant value. Now let's see the graph. Now when you plot the graph of sin I versus sin R, what do you have? Sin I will be in your vertical axis, y-axis, while your sin R will be in your what? X or horizontal axis. You find out that you have a straight line graph which passes through the origin. And when you find the slope of this graph, it will give you that constant, which is 1.5. So the slope of this graph gives you the refractive what? Index. The slope of the graph gives you the refractive what? Index. Now we have found out the investigation of the laws of refraction using our what? Optical pins. Now we look at the assignments. Our assignments: use the tabulation of angle of incidence I and angle of refraction R given below to verify Snell's law. So you are going to use this angle of incidence given and angle of refraction given. Use it to verify your Snell's law. Remember the Snell's law: the sine of angle of incidence, the ratio of the sine of angle of incidence to the sine of angle of refraction is what? Constant for a given pair of median. Now in our next class, we are going to continue with what we call the real and the apparent depths. Real and apparent depth. Thank you once again. I remain your teacher, Mrs. Okuma I N. See you next time in our next class.